Section 1. The Information Age, shaped by data structures. We live in an age defined by information. Every click, search and interaction generates vast amounts of data. This data explosion fuels innovation across industries. From self-driving cars to personalized medicine, data is the driving force. But raw data is useless without efficient ways to organize, access and manipulate it. This is where data structures come into play. Data structures are the fundamental building blocks of computer science. They provide the frameworks for storing and managing data in a way that enables efficient processing and retrieval. Choosing the right data structure is crucial for optimizing algorithms and building high-performance software. Among the many data structures available, linked lists stand out as a versatile and powerful tool. Linked lists offer a dynamic and flexible way to organize data, making them suitable for a wide range of applications. Unlike arrays, which store data in contiguous memory locations, linked lists connect data elements using pointers. This unique structure gives linked lists several advantages, particularly when dealing with dynamic data sets that change frequently in size. Understanding linked lists is essential for anyone looking to delve deeper into computer science. Their versatility and efficiency have cemented their place as a cornerstone of modern software development. As we generate ever-increasing amounts of data, the importance of efficient data structures like linked lists will only continue to grow. Section 2. Linked lists, a dynamic approach to data organization. A linked list is a linear data structure. In a linked list, elements are not stored at contiguous memory locations. Instead, each element points to the next element in the sequence. Each element in a linked list is called a node. A node consists of two fields, data and a pointer or reference to the next node. There are different types of linked lists, each with its own characteristics and advantages. Singly linked list. Each node points to the next node in the sequence. Traversal is unidirectional, from the head to the tail. Doubly linked list. Each node has two pointers, one to the next node and one to the previous node. This enables bidirectional traversal. Circular linked list. The last node points back to the first node, creating a closed loop. Linked lists differ from arrays in several key ways. Arrays store elements in contiguous memory locations, allowing for random access using indices. Linked lists, on the other hand, do not require contiguous memory allocation. This makes them more flexible for inserting or deleting elements, as only the pointers need to be updated. However, linked lists have some drawbacks compared to arrays. Accessing an element in a linked list requires traversing the list from the beginning, which can be slower than accessing elements in an array using indices. Additionally, linked lists require extra memory to store the pointers. Section 3. Linked lists in action, real-world applications. Linked lists are used in a wide array of applications, highlighting their importance in computer science. Their dynamic nature and efficient insertion-deletion operations make them suitable for managing dynamic data. One of the most common applications of linked lists is in implementing stacks and queues. These are abstract data types that are used extensively in computer science for managing data in a specific order. Linked lists provide an efficient way to implement the push and pop operations of stacks and the enqueue and dequeue operations of queues. Linked lists are also used in operating systems for various tasks, such as memory management and process scheduling. For instance, they can be used to maintain a list of free memory blocks or to keep track of processes waiting to be executed. Their ability to easily insert and delete elements makes them well suited for these dynamic environments. In addition, linked lists are used in many everyday applications. For example, they are used to implement music playlists, photo galleries, and undo-redo functionality in text editors. Their ability to maintain order while allowing for efficient insertions and deletions makes them a natural choice for these applications. Section 4. The future of data structures, linked lists, and beyond. The field of data structures continues to evolve, driven by the increasing complexity of data and the demand for faster and more efficient algorithms. Linked lists, while a fundamental data structure, are not without their limitations. Researchers are constantly exploring new data structures and algorithms that can address these limitations and improve performance. One area of active research is in developing hybrid data structures that combine the advantages of linked lists with those of other data structures. For example, skip lists combine the efficient insertion and deletion operations of linked lists with the fast search capabilities of balanced trees. Another area of development is in the use of parallel and distributed data structures. As we move towards increasingly parallel computing architectures, traditional data structures like linked lists need to be adapted to work efficiently in these environments. Despite these advancements, linked lists are likely to remain a fundamental data structure for the foreseeable future. Their simplicity, versatility, and efficiency make them an indispensable tool for any computer scientist. As we continue to generate and process vast amounts of data, the importance of efficient data structures like linked lists will only continue to grow, shaping the future of computing.